Computation workshop. Don't worry, there will be more in the future. And so as maybe you've noticed, the program has turned a little bit more toward practice today, we'll see. And indeed today is going to be showing representation about how a lot of these foundational and beautiful ideas in secure computation can be further made beautiful and also used in the real world. So first up, we have Abhi Shelat, who will be talking about the modern anonymous credential.
Thank you, Ilet. And in the tradition, we thank our hosts and our sponsors and our inspirers. This is, my partner is an art historian, so she classes me up, Mike, it's the wrong way. So this is a painting and it sort of captures how I feel about this. Like, we're sort of juggling these things and we're trying to build these things, and then there are a bunch of people, like unhappy people that don't like because their scheme isn't being used. Some people over here, some people saying, wow, that's really cool. So that's how I feel like we're in the village fair. And this is, by the way, joint work with my collaborator, Matteo Frigo, and both of us are Google. And interestingly enough, both of us share the distinction of being a TA for Silvio. So that's kind of our commonality. Okay, so in the tradition of thanking people and in reflecting on the 10 years of Simons, I'd like to basically point out this email from 2016. It's Alistair, and you can see, CCs, etc. We're full. Okay, this thing was full 10 years ago. That's great. That's fantastic. But you know what? Someone had asked them, like, can we basically have these 3 undergraduate students basically join? And they're like, let's deliberate that. You know what? It seems like it's a good cause. We can admit these 3 as an exception, as long as there are no other exceptions. And I think this email highlights 3 things. First, this is a great, Jim and the people who created this institute are fantastic. You have to invest more resources than you think you're going to need. So 3 people came. All 3 of them went to graduate school. 2 of them immediately dropped out. Okay, but the 3rd one is in the audience here. She finished her undergraduate. Okay, then she did her graduate degree. Then she did a postdoc, and now she is a professor. And that's my student Isa, and that is one of the best things that happened in 10 years for me, was working with her, right? So that's on reflecting on this institute. I think that story is probably, copied over many, many times, because many of the speakers were students essentially several years ago. Anyway, here is my topic, all right? So we have Alice and Bob, but all the people in this identity community, they have Erica and John, okay? Erica Musterman is like our Alice, okay? And Erica has some ID like this. This is a classic ID. She's very tired of carrying it around, okay? That's an inconvenience to her, but we really don't care about the inconvenience part as researchers. Like, the thing I'm worried about is that right now on the internet, I'm sure all of you have done this, have handled this issue. You're asked to basically take a picture of your ID, okay? I don't have one, but you're supposed to take a picture of it and upload it. And immediately you know what that means, right? That means every state level actor in the entire world has a copy of your driver's license. You should assume that when you do that. And I think that's an unsafe situation to be in, right? So right now, why do you have to upload a picture of your ID? Because that is how we disclose attributes about ourselves, right? It hasn't changed since 1997 or 1991 when the web started. And that is the problem that I'm going to talk about. Now, I didn't start this discussion, of course. Oh, by the way, this is not just my ruminations about this. If you go on Reddit, you'll see all these people. Adventurous Diver 587 is like, you know what? The site asked me if I should upload my ID. I'm like, I don't think that's safe. And maybe should I do it? And they ask Reddit. Like, now they ask ChatGPT, so you can't Google for it anymore. But this is a real problem. Which one? Oh, yeah. Yes, great. Right, so the idea here is, oh, wait, okay, yeah. The idea is a digital credential that we've all sort of understood, right? That after some ceremony, some like big server, some big issuer essentially gives you some digital ID. The data is kept on your phone. It's private to you, right? And then later on, you can sort of present this digital ID, and you can do this both in person and online. This is the system that people have envisioned, right? And cryptographers envisioned that in 1985, right? So 85, and there are a bunch of works starting from there on this idea. And the critical idea is that you have a digital ID, so you can sit on your phone. Moreover, you don't have to disclose all of the attributes like when you take a picture of it. You could selectively disclose some particular aspects of it. That was a key feature. This idea has been around in our field. We've written tons of papers on this, but nothing had happened. However, in 2016, this group, ISO, IEC, TC, Working Group 10, blah, 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 right? These people thought, this is a real problem. We should fix this. Now, I've met these people who work on this stuff. They're very serious people, conscientious. They really, really care about this problem. And you should think about, while we were in 2015 talking about FHE and IO and all these other things, right? They were actually trying to solve this problem of digital ID. And nobody was going to listen to them, right? Nobody was going to listen. There were no cryptographers involved in this type of thing. But they decided, without any real power to change the system, that they should work on this particular problem. And they, in fact, knew from the beginning, so I don't know who to attribute this idea to, the fact that our, teaching of undergrads over the last 30 years has created this idea of privacy and so forth. They had the idea of selective disclosure in mind, not zero knowledge, but selective disclosure in mind when they designed these type of things, okay? And just like Mike, right? Yesterday or Tuesday, we really hated rounds, collapsing them, right? That was one of our worst, we really hate rounds in this community, right? These people had the same instincts that, even 4 rounds are good, 2 rounds are definitely better. And so they basically, just like cryptographers, had a real sensitivity to the round complexity of these protocols. Okay, so what did they do? They actually came up with this protocol well before it was deployed. They designed these type of things, no cryptographers involved. It has 2 rounds, and I'm going to explain kind of what this is, because in fact it's now on your phone right now. It's like everybody, actually Apple and Google, they're using this, and it's to me a natural question. Cryptographers were studying this 30 years and nothing happens. These people are not cryptographers, but serious people. They study it, they use the techniques they know about, and they actually get something deployed and launched. And so that's like a question. I wonder how we can change that. But anyway, let's talk about what their protocol is, right? So here is a relying party RP, the website. It makes a request, so sort of adaptive, adaptive ZK is also, adaptivity is already part of this. The theorem statement is adaptive. And they're requesting, for example, age over 18, and they also have this idea of this transcript. I'll explain what that is later for preventing replayability, that type of thing. And the response here is that essentially you give this selectively disclosed protocol, again, 2-round message. I'll explain exactly what they have in mind, okay? So here is an example of the credential that they've designed. It's a string, and essentially the issuer signed this particular string, but let's look at exactly what the string is. If you want to sort of parse it away from what the actual bytes are, essentially what they're doing is signing a sequence of commitments, as well as some expiration date and some metadata about the thing. These things right here are what they call salted hashes. So this green one right here is essentially, this green is the hash of this. It's like, they're trying to build statistically hiding a commitment, right? Without, just from like basic principles. So they hash some random nonce. There's like some salt right here. This part is a salt. And then they also encode what the attribute they're saying, age over 18, and then true. And of course, because of their expertise, they do this in a very complicated way using like Seaborn encoding and all this sort of other stuff that they think is important and may be important. But the ultimate cryptographic idea is that as they essentially sign a sequence of these salted hashes, right? Okay, good. And so now how does the protocol actually work, right? What you do is, you get the request of I need to see age over 18. The phone or the user basically looks at their credential. From the issuer, when they get the issuer, they actually get, in addition to this salted hash externally, something that's not signed, they get all the pre-images of these, of these hashes. And now your phone basically looks through, sees, do I have this particular attribute under this particular namespace, blah, blah, blah. Yes, I do. So what I'm going to do is send over the full MDoc, which is, I'm going to send over this document in the clear. And then I'm going to basically give the pre-image for the thing that I want to show, the selective disclosure part. And then I'm going to do some other stuff, which I'll explain in a second, right? But I would say that's an elegant protocol for if all you had, which we love cryptography that just depends on SHA-256, right? And if that's all you have and you don't know polynomials, right, this is the limit of where you can get. But it's already pretty sophisticated. The only extra idea that we're going to add here is essentially Reed-Solomon encoding. And then we get the extra step. But without that, this is great. And so why isn't this enough? This protocol isn't enough. There's one other very critical security concern, which essentially, if you deploy credentials to people's phones, you basically have a very serious attack, which is that people can root these phones, copy these credentials, and move over these credentials. It becomes a more problem when you have zero knowledge on top of this, because of course, then it's very hard to revoke the credentials that have been copied, et cetera. So you can't tell what they are, right? So they immediately thought, these ISO people, they immediately thought that this would be a serious concern. You have to make sure that you don't just copy credentials, and moreover, you don't just like replay. You get a proof from somebody else's phone and then just replay it all across the internet, right? That's a pretty reasonable concern. So what they do is they, without any other tools, they rely on trusted hardware. And this is this notion called device binding. And here are the ideas. You want to try to chain the ID to exactly the phone. And what you do to do that, you essentially use some special hardware on this phone. Every phone essentially has this type of secure element at the bottom layer of it. This secure element, unfortunately, and this is where the whole problem of my problem comes up with, this secure element only does two things, which is what? Sign what? Sign with RSA and sign with ECDSA. And that's it. And then of course all the Android layers and so forth, they essentially build on top of this. This is a critical problem. You cannot put bilinear pairings, you cannot do bilinear pairing operations in the secure element without changing every phone in the world. Which maybe a cryptographer could say, that's reasonable, right? Eventually, there's nothing in our DNA that says we can't do this. We went to the moon, we could do that, right? So, okay, so I was going to give you a little example of, so what exactly happens and how is this exactly used? Oh, yeah, question?
For the deployed versions, all of these predicates are chosen kind of ahead of time. And they're chosen by the issuer or by Google or?
The attributes?
Yeah, they're like what the things you could display.
Good question. So these ISO people have defined essentially, they've gone through this. This is why they quibble about this. Should it be age over 18? Should it be age underscore 18? So that's the kind of, a lot of discussion is about that. But they have a list of about 50 things. Okay. And then you can, of course, propose to add some other attribute. But then we should all agree on what the semantics of date of birth is versus like age in years, that sort of thing.
Who signed this stuff?
Issuers. And so currently, the only issuers we care about are state-level issuers. Like, I'll show you an example, but like essentially passport agencies and DMVs and European states. Okay.
In this, Abhi, this trusted hardware exists also in very cheap phones, or it's only for mid-range?
Great question. So I did a query using my powers. Like, since you're at Amazon, I have powers too. I'm working at Google. Among the phones that are less than $400, only 1% of them have it. So that is a big problem. And in fact, that is one of the things that it's going. So now there's this idea of a cloud. So this has caused its own problems.
How many phones fall under that?
I have to do another query for that.
If we went to the moon, we can spend $400. Right?
Not enough.
So it depends. So that's kind of it's a loaded question because every phone that can make a phone call has a SIM in it, which has a secure element and so forth. But it's a question of like how you can access that.
But you mentioned it passive, but the cloud solution will be. So what is the big barrier there to switch to cloud as opposed to using hardware?
Oh, because then you're phoning home. So if you use a cloud, so the whole point of privacy is that when I log in or do something to some website, it's me and the website, and that's the only person who knows.
And right. I mean, we will have to do something privacy preserving there as well, I guess.
Oh, well, the metadata, you can't avoid the fact that I had to call somebody to basically say that I was about to use the internet.
Sure.
What if I can do liveness check from the phone?
What do you mean?
Like I prove facial recognition under zero knowledge.
So this question, when you say the secure element, there's various meanings of this, various levels of security for this. And every phone also has a trusted execution environment like SGX. So depends on what sort of hardness assumption you want to believe and what sort of level of assurance that these people want to accept.
Can I also ask, there's also an issue of multiple devices, no?
What do you mean?
I mean, the data can be in only one phone. What if I have to log in through my laptop when I don't have a phone or something like, or I'm somewhere?
I'll show you a demo. And so yes, all of these things have been considered. You can have certain credentials on multiple devices, and you can use these credentials cross devices. I'll show you the example in a second. What I wanted to show you was how the issuing process works. Is anybody interested, or should we just skip it? So you have to do this little video of like, the DMV, they know you because they have a picture of you already. That's a requirement. And you essentially, to onboard yourself, your phone, essentially, you have to take a video of yourself, move your head in random directions, upload that. The DMV, the issuer, has to make sure that the person that you're claiming to be, that you have a photo of, is the same person that's in the video. They do that through their whatever mechanisms they want, AI/human/whatever. Then your phone generates a secure, generates a public key right here, and essentially sends that along. And then if the DMV is certain that you're the same person, they give you a signature and they send that back to your phone. Is that okay?
Is deployed?
What?
Is this deployed?
Do you have an Android phone? Yes. So I was hoping to show a live demo, but it should be on your phone by today. It's being like pushed out. You should be able to use this. I wasn't able to get the demo to work, but
How is this called?
what?
How is this called?
Okay.
I'll show you offline. ID Pass. Download Google Wallet, and then if you have a passport, you can do this process here today. And then, well, okay, I'll skip that. Changing these layers takes 20 years. 5 years is something because the thing is recorded, but takes a long time because you have to coordinate all the people who make phones. All right. So
I have to trust the person who built the phone, right?
Yes. So you have to trust. All of this stuff requires that the issuer has to trust essentially the operator of the phone. So there are restrictions on most issuers will only issue to devices that are not rooted, that have Android or Apple. So they have a bunch of restrictions on what they do in practice because they want to maintain soundness of their system. Okay. So what was the problem though? So the problem was you want to prevent people from copying credentials. The solution was you have this piece of hardware in the phone. You include essentially the public key of this this trusted hardware in the credential that you get, and you include that public key inside the credential, right? And now what is the problem? Is that this public key is so essentially So let me go back and what the protocol is. Relying party asks for this type of stuff. They also make a fresh transcript, like a challenge. They give a nonce essentially. The device responds with the full MDoc, a pre-image for the thing you want to say, and then a signature under the device public key, which is bound here, essentially on this particular nonce. And that's kind of that's what the protocol is. With no analysis, that's what it is. And then, of course, the relying party makes these 5 checks. You can sort of see where I'm going here. This is a problem, natural problem, right? Because now that you're giving this full MDoc to everybody, right? Forget about your third-party cookies or whatever, right? Every time you use this credential now, essentially you have a device public key of your phone that cannot be extracted from your phone. So not only does the relying party know who you are, but they know which phone and which device, essentially, if you put this on multiple devices that you are using. So they know that, were you in the shower, were you there, were you at your desktop, etc. That's not great. So again, this is before cryptographers got involved. What did practitioners essentially suggest? They're like, well, what you could do is essentially use one credential for this relying party and a different credential for another relying party. Okay? So for everybody that you present to, use a different one. As a result, you can't be linked between service providers. But of course, there's still a problem with that, which is that that doesn't prevent the biggest threat to this type of thing, which is that the issuer itself can subpoena the service provider, and since they signed all of these things, they'll know exactly who used which credential where, if they were to subpoena this. This is a real threat, because if you want to do some sort of if you're in the state of Texas, for example, and you have an attorney general that can subpoena you there and get all your records, this is a problem. And in fact, last summer, many cryptographers wrote a letter that said EU was going to do something similar to this. We wrote a letter, and that feedback was taken seriously, and new suggestions were a thing. Now, how do you fix this problem, starting as a cryptographer? How do you fix this? We know we have a lot of cryptography that can solve this. There's 25 years of it. Many schemes like BBS Plus, et cetera, that are essentially designed exactly for this problem. However, as you asked, where is it deployed? All of these states have spent money basically building the thing that the ISO people specified and convinced everybody to kind of do. This is deployed already. You could get these things on Apple. You can get them on Android and so forth. So what could you do? Ask them to say, just junk all of the thing that you basically used and built and try to use this other scheme that we'll try to design in the year or so, right? That is essentially not a feasible option. And that is essentially what the point of my talk is. The modern anonymous credential is not essentially cryptography greenfield. It's actually essentially take whatever the legacy people have done and essentially take the right ZK, generic ZK narc here, and essentially build a ZK that can gracefully deploy on top of any of the legacy schemes that are there. And that was the problem statement, and this is my attempted solution at it. And I would love your feedback on this.
I think even without that, if you want to device binding with BBS, it's not possible, right? So because
well, it's not possible. People don't know how to do it, but you could actually put the whole thing in the secure element and do it.
Yeah,
Yeah.
But then you need to support a pairing-friendly curve.
Yes.
It doesn't. Yeah.
Yes.
Same problem exactly.
Question.
For unlinkability,
Michele.
I thought the big problem was not a subpoena, was just unlinkability across many sessions. Am I understanding badly?
There are two problems. Unlinkability across many
Right.
replying parties. So
Okay,
two relying parties could essentially, data brokers could, okay, but you also have, even if you use a different credential for every session, you still have the problem that the issuer, the state, the issuer of the credential, they know everybody's device public key. They can essentially subpoena logs and then essentially figure out who is using what where.
And using blind signatures, like, wouldn't solve it?
Using blind signatures, well, the problem is we don't know a good blind signature for ECDSA.
MPC workshop.
And that is, of course, changing what they're doing. So the whole problem is they will do what they do, and we will add privacy on top of that. And that's, okay, great. So, so what is the overall solution here? It's something like exactly the first message comes back, and instead of sending the previous stuff, you send back essentially a ZK proof, and then of course some like the other information that's needed to verify the public parameters of the ZK proof. And then what the relying party would have done by themselves here, checking all of these 5 steps, this ZK proof just checks all of these 5 steps. So that's the recipe. To win in this game, all you need to do is come up with a scheme that can do this green box efficiently on the phone. That's the game. However, there are some differences between what our theoretical literature says, right? We love snarks, we love the succinctness of it, but actually this is a David Goliath situation. You have a very small prover and a very large verifier. And so the whole idea is, succinctness isn't necessary. It's actually prover time that you're optimized. You can use any scheme that's concretely, efficient for this type of thing. There are other type of considerations. So for example, it's my opinion and sort of backed by sort of the practical people I sort of talked to, trusted parameters are essentially impossible to set up. So yes, Zcash did an amazing thing. They got the guy in the desert and over there, and they did a ceremony and they created this really billion-character string to do all this anonymous transactions. That will not work with issuers and DMVs. They simply will not collaborate with one another. Like Texas, you imagine them dealing with anybody else. It's like it'd be, okay, actually it's recorded, so I didn't mean Tejas, not the state in the fictional Lamb of Utopia. Okay, right, and you can't also, the other psychological aspect that we forget is you can't just ignore all those people that got this actually from essentially a Word document into production. Those people, you can't ignore their work. They have actually considered some corner cases that we wouldn't have. You have to sort of understand their expertise. And of course, the other thing is issuers are limited. So these are DMVs, we should not use any protocol that requires them to do internet scale work. And so first of all, they shouldn't be in any online flow because that of course leaks privacy, but you also have to limit the amount of work they do. And this is also true for the revocation process. You have to support revocation and so forth, and they can't do like internet scale or like even O of N work every day is too much for them. So you can formalize exactly what that means. And then the other interesting restriction is that most organizations, we had a first version of this that actually had much smaller proofs, used elliptic curve commitment, all of the techniques you know, and that was rejected because most organizations don't want to deploy anything that isn't, doesn't have some sort of plausible post-quantum story. And of course, engineering type of things. What? This is true?
Yeah,
absolutely.
But post-quantum, the organization currently are like...
Yes, because the first version of this, yes, this is absolutely true. I can give you a list of like my organization, Google, is certainly in this particular, Mariana, I don't know, you could have different opinions because Google's a federation actually, it's not like but Apple is also that case and EU is also that sort of case. Everybody's asking for this. They don't want to deploy anything like that.
What if LWE gets a phone all the time?
I know, that would be great, right? Chaos.
It almost happened.
What?
It almost happened.
It's almost happened with ELA's work, yeah.
Then they accept.
Well, there are other strategies, right? There's these other SHA-based signatures and so forth that would avoid that. But okay, all right. So this is more fun than okay. So prior work, we did a bunch of stuff. It was nothing really worked there. We thought we were looking for this particular object. We looked at eventually all of these type of things. I do want to get to some of the technical approaches. Question?
Is there any reason that you have to do the token issue or the issuance over the internet? Like, if I have to go to the DMV in order to update my car title all the time, like, why not just in person?
Have you been to the DMV?
Yes, like I have to go. That's kind of the whole point.
Well, hopefully it's a once-in-a-lifetime situation. I haven't gone in years, except for my son here got his learner's permit. I had to go for that, but yes, but. Well, yeah, I don't think it's practical to have essentially repeated.
That was like a design constraint. You have to issue over the internet, essentially.
For scale, to have this work at scale, yes. Okay, so I'll tell you essentially the recipe we used was the oldest recipe that I could find except for GMW. And that is essentially you run in, this is the everything provable recipe, which I absolutely love. All you do is select 3 pieces like an interactive protocol, a commitment scheme, and sort of a special zero knowledge for essentially those 2 objects. You just pick those objects, and essentially these are our choices. So I call it layered sumcheck because just like garbled circuits, people just say garbled circuits now. There's a ton of advancements from what Yao came up with, right? And so layered sumcheck is kind of what I put GKR as to Yao as layered sumcheck is to garbled circuits. So that's what I call that. And of course, the commitment scheme that we used previously would use to essentially an elliptic curve commitment with sort of an inner product argument like a bulletproof. And now, because of that feedback that we received, we use Ligero, and it only uses SHA-256 and so forth. And this is essentially the simple protocol. You first you first pick a random pad and then you commit using Ligero to some commitment there. Then you run this sumcheck, this layered sumcheck protocol for whatever circuit that you're trying to verify with the public input and private input right here, and essentially this is just having the public input. And you run it in sort of an encrypted or committed mode. So whenever the sumcheck message would have sent MI, you actually send MI plus the pad that you've committed. So this produces essentially an encrypted transcript of the sumcheck protocol. And then you essentially run Ligero prover on this commitment and essentially the verifier of the sumcheck transcript. Now, if you remember with sumcheck, or layered sumcheck, essentially all of the checks are linear. You basically check that P0 plus P1 was the value from the previous round, and then you interpolate the next round for the next challenge, etc. The only multiplications you do are between layers. So when you go from one layer to another layer, you have to essentially do one multiplication to do the reduction, right? So essentially this statement that you're doing, the sumcheck transcript is, you all know it's sort of logarithmic, depth times logarithmic in the width, and those are all linear checks. And then essentially depth multiplication checks. So it's very, very small. To give you concrete, we check like maybe 22 multiplications and a few thousand linear constraints, right? So that makes a very, very small verifier right here that you apply Ligero to. Why do we do this instead of just Ligero? Just doing Ligero would be simpler, and in fact, Muthu is going to talk about all the other problems you can solve with this type of recipe. And the reason we don't is because here Ligero, this image is wrong. You only commit to the multiplication gates, but you do commit to all of the multiplication gates. I'll give you some concrete information about how many multiplication gates are involved in the circuits that we're doing. Roughly millions versus we're doing like 9 or 22. Okay, yeah, this Ligero with layered sumcheck, you just commit to the inputs and the sumcheck transcript, which is much smaller, right? So if you believe that the NTT, which is the only nonlinear step in this entire proof system, is the bottleneck, then in fact, doing this type of approach, reducing the size that you have to commit to, that's sort of like the key design point in this space. Now, of course, we're exploiting the fact that you're not committing to the entire transcript of the computation. And so, of course, you open yourself up to this very clever recent attack by Ron and co-authors. And of course, we avoid this because we're verifying a circuit instead of computing it. So we're very low depth. And of course, we also make our random oracle function to be sort of, so these are all heuristic arguments, but they heuristically avoid those type of attacks. And this is something that does keep me awake. And this is, in fact, a good thing for theory to look into more. But that's the way it is. What about, so Giacomo? Yep, there he is. We've talked to him about this. Why use this versus that? I ran some experiments. This is the proofs are about the same size. So essentially for our parameter size, they are roughly the same size as Ligero, and the prover takes a little bit longer. So since we are trying to minimize the experience, that is essentially, as Ron likes to say, all the complexity for little gain. Lookup arguments, we've also studied those type of things. I would love to be corrected on this. So that's kind of why I'm presenting to this audience. I'd love to understand if someone can think of a way a lookup argument could improve the thing we're doing. But again, we can't see. Huh?
Something more basic. Like, what is the statement that you're proving?
Yes, I'll show you right now. This one right here. So just give me 2 slides to, yes, let's skip that. Remember, this was our original protocol. This was the legacy protocol. We can't really change. We changed a little bit, but this is essentially the idea of it. If you look at these 5 steps, I've broken it down into this statement, which is roughly the type of thing. So you have the public values, which are the issuer public key, the attribute, the transcript, the time of the proof given, and then this is the private witness, the MDL string, hashes, signatures, etc. And these are the statements that you're checking. So, for example, the SHA of this document that you have is this: the signature verifies. This signature verifies on this hash with this public key. Of course, you can hide the issuer. So if you're one of 50 states, this model makes it very easy. You just mux on the 50 state keys there, actually very little cost. And you do that type of thing. Then you do this parsing part. You have to parse this damn CBOR encoded document. It's like ridiculously hard to do this, but it can be done. My colleague Matteo is like excellent. He used this parallel prefix approach to parse this. It's like again a great idea from theory and so forth. And then you have to, of course, do the salted hash. Then you have to check the device public key transcript. Then you have to check that the credential is valid today at the time that the proof was generated. So all of this stuff is easy. This right here is the only really expensive part.
So if you need it only for commitments, you could use something like almost linear commitments or something like this based on the coding theoretic assumptions. Wouldn't it simplify things?
So say that again. Like which part do you want to replace? Like where? You mean the salted hash part?
The SHA. I mean, if SHA is only used as a
No. This part right here is basically how ECDSA is specified. We can't change this.
I see. You cannot change it.
Yeah. And what a gift ECDSA is, right? No proof, nothing, but it works. So gift, SWOT, I would say that's a consequence of patents. Okay. Okay, this I think is the demo. It's from a few months ago, so it's like a debug version, but and it shows the hardest case, which is, here, let me pause it, oops. Let me pause it. This case is like you're on a laptop. You're trying to do something that requires you to verify your age. I'll let you guess what that is. You have a credential on your phone, and you need to basically convince your browser that you're age over 18. Okay, so this is a sample website, and it's asking for birthday. You essentially take your phone right here, and you scan this thing right here. It uses the same mechanism as passkey login. And most of the latency right here is the Bluetooth connection between these two. It'll ask you some questions about which driver's license, you could have multiple, which driver's license, who you're going to give to. It asks for your biometric because remember the secure element needs to be invoked in order to generate the device public key. It's going to produce the proof, it's already done that, but now it's going to connect and essentially send the proof back here. And essentially now if you scroll down here, it show the proof has essentially been sent. That is the experience. The UX people say it needs to be less than a second to produce the proof. Our proof maybe right now takes about 800 milliseconds on a Pixel 6. It takes about 400 milliseconds on an iPhone 15. So it fits well within that thing. Has a bunch of restrictions. I told you 231 bytes, credential size, Unfortunately, practitioners are going to put all sorts of stuff, like your blood type and so forth, in your credential, which will make that document bigger. So we do need to essentially improve that as well. Let's see. Okay, so let me spend a little bit of time. Yeah, question?
So if I parse correctly there, it seems that the age over 18 was actually an attribute itself.
Yes.
So can you, I guess you're going to say something about more general, like a disclosure, if you have a function of an attribute instead?
Yes, of course, when you have a ZK system, you can build any predicate that you want, right? Yeah. However, as I told you, we're building our thing on top of legacy ISO. So unfortunately, they can't ask for any predicate. What they can ask for are the attributes. The way they designed it was you had a series of attributes, you can only ask for equality. Of course, we've mentioned to them that we can do more complex things. Now, what does that create? There's no favor from that. No love is, essentially, now people have suggested some sort of DCQL, some sort of SQL-like language that you can ask on your thing, right? Instead of some simple, like ands and ors, like, give me a 3CNF with 7 clauses or something. No, it's SQL. So unfortunately, no good deed goes unpunished if you ask that question.
Yeah. No, but the question is also nice for us, like what is the efficiency that we can tolerate? Right? I guess most of the predicates are pretty simple.
Yes, most of the predicates are less than or equal then. Now, the thing I'm proposing is ZK tax. So because you saw those people basically copied all of your tax returns to some kid's laptop, right? So now you can assume that they are like essentially by nation-state actors have all of your tax reports, right? Wouldn't it be great if there was a system where you could essentially prove your tax amount was this much and that you're paying that amount without essentially disclosing all of that? That, of course, requires a more sophisticated thing and probably a more sophisticated ZK than this, like some sort of VM-based thing. However, this is the stepping stone. Okay, so I want to talk about 2 ideas that make this work. So it wasn't just gluing stuff together. These and this rolls right into Srini's talk from yesterday. When he was giving his talk, I was like, wow, did he figure out exactly the same thing, except it was slightly different, right? So here is, and I'm also like, so here's the textbook way for implementing Reed-Solomon. I think when you're given an array, right, so Reed-Solomon is essentially the critical step in the Ligero in sort of almost all hash-based proof systems. You need to basically do some sort of encoding step. And you interpret this array as coefficients. You apply the NTT to compute the evaluations at the roots of unity, and then your Reed-Solomon code is just the P at the roots of unity, right? Would you agree this is the textbook approach? We are going to say this is not the right way to do it. There's a better way to do this, both from engineering and asymptotically, or not. So this works great when the roots exist. However, the problem we have, in fact, the problem that many of the prior works had with proving things about ECDSA signatures is that so much ECDSA and not a root around. So P256 is a specified curve for ECDSA, and if you look at it, there's essentially no good roots for you, right? And these are the other ones. There's the K1 curve, which is used for crypto people. The German people have brain pool, and then these other people who think 256 is not good enough. None of these have roots. So we made an observation that worked out well for the P256 case, which is that the quadratic extension of this thing does, right? So the quadratic extension has 97 roots of unity here. So you can, for P256, 2 to the 97, you can actually essentially do what we were saying before in the quadratic extension. You could keep all of your evaluations in the base field, right? So essentially the size and everything would, However, if you do it based on the textbook, this thing right here, right? These omega things are field elements, extension elements, right? So these evaluations are going to be extension elements too. You actually blow up the size of your thing. So we didn't like that. And in fact, the benchmarks show this type of thing, right? So for example, the 128 field takes about this much, and normally, if you just look at Srini's math there, right, if you go from 128 to 256, you should get a blow up of 4, right? But here it's like more like 10, and that is because there's another blow up of 4 because of the quadratic, or 3 because of the quadratic extension if you use Karatsuba. And so that's essentially what explains that. Now we do something different. Those numbers are actually, there would be nothing you could do for these other curves, right? You could use Nussbaumer's algorithm. You could use the elliptic curve FFT, which is a great theoretical result, but I haven't found essentially elliptic curve for any of these type of things. The Nussbaumer thing has a log penalty right there. That's pretty big. That's like a factor of 16. That's not good for the phone. So let me tell you how we handle this particular problem. How and what is the problem? You need to support every curve that any government could essentially theoretically use, and needs to work on the phone. So, and you're using a only hash-based proof system, so you have to use Reed-Solomon or some sort of error correcting code. So we are going to redefine what the Reed-Solomon is. So given, instead of the input being coefficients, we're going to look at these as evaluations. You'll see why we do this. And then the Reed-Solomon operation is like, if I give you the first k operations, you give me k plus 1 to n, some like different set of operations. So you just interpolate, right? So we want to say, instead of just entity, do interpolation. This is a nice formula. If you work it out, this is the Lagrange formula for interpolation. If you give in these first points and you want to compute this point, then it's like this. Okay? Now, if you just do one little math exchange, Google query, you can actually, and if you work it out yourself, you can actually turn this formula just through simple observations into this formula. Okay? Now, what is nice about this formula? What is nice about this is that it is a convolution. So here you have the k minus I part, and here you have the I part. This is just a constant right here. And if you see it, you see it, but this is like how I like to see it. So this should be a picture proof of it, right? So if you're actually evaluating this type of thing, what you want to do is get evaluations at 6, 7, 8, 9. You want to get them in an arithmetic sequence, right? Then what this turns out to be, this right here is a matrix of this form, right? Blah, 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 7, 6, 5, 4, This matrix is circulant, right? So this, I remember having this as an undergraduate problem. It's in CLRSW, right? How do you do this? Like, how do you evaluate a circulant matrix using the FFT? And of course, you turn the circular convolution into a linear convolution of twice the size, et cetera, right? But you see, the point is you take the input points, you apply a linear set of operations here to get this matrix, and then you apply an FFT, a convolution between these two steps, okay? So that's how we're defining it. At this point, we haven't solved anything, but we are about to. The nice thing about this is defined. If you define Reed-Solomon like this, at least when you're writing a spec for the standard, when you define it this way, it is defined everywhere all the time for any particular field. And that is a very good thing. So no matter how you compute this evaluation, it exists and it works. And it's also space efficient now. So even if you use a quadratic extension, if P is in the base field, even though you use an entity in the quadratic extension, these evaluations will be in the base field too. So immediately we save just for our P256. But here's the idea. Okay, so instead of doing, these operations are in the field, whatever field you are doing. Let's now move to the integers. And this is why Srini's talk, you'll see, is like essentially very, very close to this. So just to be concrete, I turned those integers for the particular small prime. You look at these as integers, right? And you look at these as integers, and you do this operation over the integers. Okay? And then after you get the integers, then you do a reduction mod p, and then you'd get the same result, right? Okay, good. Next step. Now, instead of since you're doing it over the integers, of course you could do it over CRT. Just like Srini was saying, the CRT is always a winner. And so you know that these integer results, if this is a group in P, this is a group in P, the result is 2P, right? So 2P bits. So you just need to do a CRT that's big enough, 2P bigger. It's not exactly 2P because it's a summation over here and you have these constants too. So it's a little extra, but it's very small. Okay, so good. Now, what CRT primes are you going to use? You can use any primes that together are big enough, and you get to pick the primes. So you're, of course, going to pick primes that have roots of unity. Okay? So now you pick nice primes with roots. You do the convolutions over single word over single words for these particular primes, right? And now that is fast because the basic entity algorithm works. Now you reconstruct the integers using the CRT, and now you do a reduction. Okay? And this is the thing that I thought was, so remember Srini is doing a similar type of thing. CRT is always a winner. You get t squared here though. If you just do, so what is this slide saying? If you have one word primes, you take n log n word multiplication operations, right? But in our field, 256 usually use 4 word primes, right? So you use 4 word primes, so essentially n log n times 4 word multiplications, right? And if you do schoolbook, and schoolbook is essentially the only thing that works at this particular range, then you're doing t squared multiply operations here. So again, just the basic FFT is going to do n log n times t squared, like 16 here, operations. Now, what happens when instead you do it our way? Instead, you're doing 2t, because you need twice as big, plus like extra, entity operations for 1 word primes. So essentially you're doing this many operations, and that's like a factor of 4 for 256, factor of, much larger factor for 521. So that is the asymptotic improvement, and it works really, really well. So we haven't fully implemented this because there's an extra trick I'm going to tell you about in a second. This is this is like a NTT for like one word. This is our implementation. And you can sort of see that this gap right here is kind of like on the order of like 30, right? Yeah, maybe like 16, sorry. And instead we only need 9, right? So from 9 to 16, that's a significant improvement. It goes from like 400 milliseconds to like 200 milliseconds, yeah.
You've benchmarked the CRT?
We have not fully benchmarked. I'm not going to give you any numbers, so we have some partial results, because I'll tell you the next trick that we have not figured out. So you get to pick your primes. So which primes are you going to pick? Yes, you can pick any primes that have the right roots. However, here's the next level trick, which is that all of these primes have enough roots, okay? But they are also factors of the Fermat numbers, 2 to the 2m minus plus 1, 2 to the 2 to the 2m plus 1. And if you just go to ChatGPT and ask the question, for which fields are 2 a root of unity? Is 2 a root of unity? Okay, it tells you that this is Fermat numbers. So you can look at factorizations of previous Fermat numbers. People love playing this game. Pick a big Fermat number, factor it, and post it on the internet. That game has been going for like 30, 40 years. So we have great list, and this is a great application of this. I just looked through that list, found all of these guys, and 2 is a root of unity. Now, what does that mean, that 2 is a root of unity? It means that when you're doing NTT, the twiddle factors that you do, that you multiply, you're multiplying by 2. Okay, now here is a life lesson. I'm going to ask Srini, I'm going to put you on the spot about this. Which is faster, 64-bit multiplication or a shift by a random value, shifting a value by 2, by like, let's say, k bits, where k is unspecified?
You're asking me?
Yes. As a hardware expert, which one do you think? I would have thought shifting was way faster, right? But if you think about it, when you implement a shifter where it's not just shifting by a constant amount, that's very simple, that's copying. But when the shifting amount is a variable, you actually have to have a log depth circuit to kind of do the, you first do by 2 and then to 4, et cetera, right?
But you need all the shift sides.
Exactly. So what I'm saying is that the hardware circuit for shifting is like roughly the same space and energy as a multiplication, and in fact more depth. Depends on how you do it. So in fact, it's not a clear win, but it is when you do this AVX trick. When you pack all of these things, you can sort of do one shift and shift the whole vector right there. You can get multiplications by this quite a bit easier. Now, to tell you the truth, let me explain where I got this idea. And Matteo, and I figured this idea out. We were reading David Harvey and Joris van der Hoeven's paper, trying to understand whether we could apply any of those techniques. And we never get past the introduction in that paper, because it's like a deep idea. However, we love reading the introduction over and over and over. And if you look at this particular thing, this is like the whole Schoenstrassen type of approach, right? So I would like to say that this is theory actually doing a really interesting win, because these type of algorithms people have studied for a long time, and nobody really uses them in practice unless you're doing like 3 million unless you're doing games like let's find the next, let's verify that this is a Mersenne prime, etc. However, in this application for this phone, for roughly 1 billion devices, we will be doing this algorithm, which is pretty cool. And these ideas are essentially, this Fermat idea came from this thing right here, using 2 as a thing, and Furer's thing was like combining these two. We didn't understand any of the complex stuff, but the simple stuff that I just explained does work. And in fact, I would say that like the folklore for how to do Reed-Solomon encoding is just use the NTT, and this is like always works and is always better. Okay.
Actually, I didn't follow. Why did it help that you took prime factors of Fermat prime?
Okay, so for these numbers, 2 is a root of unity. So when you do NTT, you're multiplying by the roots of unity, by various roots of unity. Those are like the twiddle factors. So now all the multiplications are shifts. So if you're computing bit complexity like those guys in that game, where your bit complexity is a number, shifting is way better than like multiplication. So that's how you get those results. For us, it's not clear that on a real machine shifting and multiplication is better, but for AVX, in fact, it is kind of, you can do 4 of those operations. Okay.
Abhi, just as a broader perspective, Reed-Solomon codes, I guess, are widely deployed in actual coding systems, old CDs, DVDs. I guess the parameter regime is very different.
Yeah.
Why are this explains
why nobody has done this before? Yeah. People who need like big prime Reed-Solomon, I think it's just us.
I see. Okay. So it's really about the size of the primes.
Yeah. And things like this circle FFT, I think all of that is subsumed by this. Using 2 to the 32 minus 1, I don't even understand why that is like a winning thing now. Anyway, Right, and then I also wanted to make sure that our math is just as good as everybody else's math, just to make sure my tables are okay. That is where our Longfellow, we're always multiplying numbers of this size right here, so those numbers are not just like an artifact of what I want to say. Let me, yeah, question?
Like there are like wind over like this kind of like techniques on field agnostic, like IOPPs, like base fold, just because they're much the big wins on those, right? Because there's like this line of work on doing IOPPs for like foldable code, which can be agnostic of the field, and the motivation was for the ECDSA, for proving ECDSA circuits efficiently.
You only get linear time. You don't get multiplicativity, which is needed in Ligero.
No, but like I mean, like the encoding of the foldable code, you can
It's
do.
not multiplicative. The code needs to be multiplicative. Like Reed-Solomon is multiplicative.
Sure, I argue you can probably avoid that.
Yes, so the idea is like, do we use Ligero just to do our 9 multiplicative quadratic checks, or do we use some other mechanism to do it and then use some other approach?
Yeah.
I would love to hear a better theory for how to do it, but practically this is a very simple thing. It's very simple and it works really well. Simplicity is there's an advantage to it. We have to convince, like this is what I spend my time now, convincing people that this is even reasonable. So already the polynomial thing is a big leap. So
Sorry,
last idea, yeah?
Following up on this topic also about interpolation, the first thing that comes to mind is the barycentric formula, not going through a CRDT with a circular matrix. Have you thought about that?
No, if you have a concrete idea that gets our same approach.
From n evaluations, I can get another one.
Yeah, same,
The
yeah.
polynomial in linear time, using the barycentric formula.
Yes, of course. You can get 1 in linear time, but we need n. We need like 4n, 8n.
Yeah.
So if you apply that just by itself, now if there's a batching mechanism that you have in mind,
Right, maybe,
great.
I don't know. Yeah, okay.
Yeah.
So, yeah.
Okay, good. So it's a tale of two fields. So ECDSA, we do our sumcheck and our proof in the F256 field because we don't want to simulate the math. And it's very, very fast and cheap when we do it like this. It's like 60 milliseconds, maybe 30 to 60 milliseconds to prove knowledge of an ECDSA signature. That's actually now a solved thing. However, it's the worst of fields for proving something about SHA-256. The best circuit we have there uses a lot of bit operations to do the ANDs and the XORs and so forth. This Galois field that like sort of Posen and Diamond and Posen, the Binius work essentially put us onto this right here. It's really the field of wisdom for binary, for Boolean circuits like SHA-256, but it's a foolishness for this type of thing. And so what exactly do? We want to basically do the best of both worlds. We want to do one proof in this field and another proof in this field. We need to do 2 proofs. Now, this is not a very deep idea. They will share some particular witnesses right here, like the E value and the device public key will be shared because these values will come from the credential, right? And they need to be used in that other type of thing, okay? And these protocols, they need to share private witnesses. How do you ensure consistency? I think the idea is pretty obvious when you put the problem like this. We just compute a MAC inside this, inside our circuit. This MAC is over GF to the 8, so it's like natural MAC. It's AX plus B in this, so it's one operation. Here we have to simulate the MAC essentially in this particular field. But if you do all of the experiments and so forth, anytime you're computing at least 2 SHA operations, it's better to use this MAC. Essentially, one MAC computation inside this big field for this type of thing is about equally complex to 2 SHA, full SHA operations, right? So anytime you're doing that, it's better to split these fields. And that's like a key idea to make this work as well, although it's quite simple idea. What are some good questions here? It would be great to have a post-quantum signature with a good proof of possession for the signature. I think that's a good open question. If you look at all the things that NIST is standardized, many of them use like SHA-256, so you'd have to give proofs about SHA-256. So all of the MPC and the head stuff, I'm not sure that works. So there is like room to co-design this type of thing. The lattice signatures have really big parameters. They're too big to put into like, could work, but I think that's a great open question. But right now, the tightness analysis, so Mihir gave a great talk about tightness and why that should be important, concrete security and being tight on these type of things. I totally agree with this because it's how we set our parameters. And the proximity gaps that I know you and Muthu are working on, I think are critical. And then even something like statistically hiding commitments, which if you look at Alessandro's book right here, you see you lose quite a bit right here. This is not something I want to lose right here, this square root thing. This proof isn't tight, but like, am I going to be able to make it better? Probably not. So somebody.
You want perfect statistical hiding, you don't care about the query bounded case.
No. Well, we would like, so we would like. Yes, but what you want is everlasting security. So I think that the only way to argue that is to essentially, yeah. So it's not the query bounded case. Okay. And like the other thing that we're working on is like, actually this is so simple that we can sort of possibly formally verify. We can formally verify some of the circuits. Sumcheck, there's already an approach to formally verifying it. Ligero is just Reed-Solomon coding with Merkle tree stuff. So is my goal, and with hopefully my magic resources, that we could deploy a crypto system that has some aspect of formal verification. And I think that's pretty critical. Okay, so I'm just at time there. I'm happy to take questions. I wish I could show you the demo, but maybe definitely by crypto, it'll be something that you could publicly verify. You could hold you hold your passports here. You get a credential, and then you can go to some test website. This does work if you're in the UK. There are places that, but it's being rolled out in a way that's hard for you as Americans to test right now. 2 weeks.
Thanks, Phil.
I would love critical analysis on this. Like, as Silvio says, cryptographers don't sleep. I'm not sleeping very well because this is, yeah.
Just a comment that I checked. It works for UK and US right now.
Oh, you did it.
Yeah.
Great. Okay, okay, great. You just did it. Fantastic.
Is the reason this protocol is not interactive because the issuer is talking to the client and then the client talks to, say, the provider, or can it be made interactive?
Well, as we like to say, like, we like to crush rounds and they like to crush them too. So in fact, I think that's a pretty like set in stone thing, that the protocol is like one message because you have to ask what you want, and then one message to respond, and then the website can figure out what to do and done. If you do anything complicated, that becomes very complicated for engineering. In particular, things at scale, keeping state is like really tough.
So I'm curious, like, who is pushing for this in the U.S.? Like,
who wants this? That's a great question. Well, those mobile driver's license, you can ask the ISO folks. That is like a thing that's happening. And now people are saying, well, so there are, in Texas, you need to be age verified to go to certain content. So, and in EU, that's also the rule. So that is one major, society has voted. They want to make sure that only, certain age restricted content is not available to children. That's something society voted for. How do you implement that? And that's one use case. The other use cases are essentially, EU has put in law, data minimization is the law. You should not collect more information than you need. So that's one thing. My friends at Amazon, they tell me that essentially there's a fraud issue with like shipping packages to like the wrong address from the person. So that is one use case too, that possibly you want to prove that this is your address from your MDL, and then that basically sets signals about like how real is this big purchase type of thing. Yeah, Evgeny?
The question about the transferability, non-transferability. So sometimes it's like legal, it's like my iPad and my phone, and sometimes you don't want to copy. How is it currently solved?
It's currently solved in that you can only have one credential on one device. So if you put your ID pass on this type of thing, then when you put it somewhere else, at least in the trusted software model, it gets revoked or expired from this type of thing.
But you can put it by yourself, or you need to go to...
No. You have to do this whole ceremony on every device that you do.
And then it just gets revoked. And is there some empiric? How would we do
This is like a real world thing. So unfortunately, there are cracks. Like you could, like in the time that you have two, you could. So there, it's not perfect. There isn't really a good perfect way to get this to work fully sound and also like something that can be deployed. There are cracks in this, but that's kind of what the current thing is. I'm not sure what the whole discussion of is if you want it on multiple devices, how that works. The idea, that's why we did that super complicated flow where on any other device, you kind of bring your device to this type of thing and do that. We'll see how the thing emerges.
I mean, that's also why I was asking you about the cloud-based solution. What was your take on that, or Google's take? Because that's one of the things that people have been thinking also because of that problem.
So the
in order
EU...
to transfer, but it seems that your concern is really metadata. But that seems to be there could be a compromise, right? Where if you have an adversary that cannot see the metadata, this would be a fine solution. Or if it's something that you exclude, just I don't know what's the thing.
It's very hard to deploy those cloud HSMs. This is how many have been deployed so far. So, and the Europeans are basically going along that particular approach because That's what the laws, basically, that's how they're interpreting them. And good luck when they deploy these type of things. For the age assurance case, those things don't need the LOA hide, they don't need the cloud HSM. And so so there might be a flow for the most common use case that's basically privacy friendly.
Is there, so when you're talking about revocation, you're talking about revocation that the issuer is doing after a time or when you get a new one? Is there, there's presumably like there's going to be a demand down the road for revocation if you're being abusive on a website. So you've presented your credential, you log in, and you do shitty stuff, and they want to revoke. Is that anywhere
yes,
in the conversation yet?
Two answers to that. Pipeline is pseudonyms that David Chom had in 1985. That solves it. This can easily do it. You can make a hash of your type of thing.
Is there demand coming from that? Like, is that part of
That's part of the EUD thing, yes. And we have a solution for that. We also, didn't talk about it, have a ZK revocation thing that it works better than accumulators. You have to talk about like practical deployment issues, and accumulators don't work, but simpler other things do work. Yeah?
For applications such as ZK tax, how likely do you think it is
Like ZK tax, yeah?
or any other cool application you think of, how likely is it that we can ship, I don't know, cool new cryptography, like polynomial commitments or something? Or do you think we're sort of stuck with, I don't know, ECDSA?
No, I do think this is a stepping stone. This is like getting this out, and I do think that more advanced people will be more willing. And yes, you have to be a dreamer, right? You're not here if you're not a dreamer. Do you want to do something? All of the dream has been crushed out of me, but there's one still ounce of it left.
I guess more broadly, I think you started this talk by saying, cryptographers sort of do all these cool stuff, but they don't get deployed. How do we get more involved in these design discussions?
Oh boy, I don't know. You have to give up your life. I don't know, like Hugo has done this a few times, and like, I don't know. So you should ask other people in the room who've had like practical impact.
So you mentioned that there's something in the works for next year. Can you share more details?
Something in the works for next year?
You said you're going to avoid ZK snarks and you'll do proper thing from ground up. So what is that project? You said in the works you're going to hopefully work towards getting away from legacy thing and doing a proper, I don't know, BBS type or whatever. I mean,
So first of all, I don't think BBS is proper. That will never work for this application because of that secure element thing. The thing that I was maybe mentioning is that what I want to get rid of is that string is formatted in some very funny way. So like the baby step hybrid argument, that's what I learned from this entire experience, is that you could start over here and then make a small change, like change that silly format from like, the way that I showed you to something that is way more compact. In fact, you could actually argue like a Peterson commitment, because the only one more permutation we know is that one, right, the G to the X. That is actually naturally statistically hiding, right? So that could be a use case for that, so essentially the thing I'm working on is replacing that SHA, like that crazy string nonsense, with a hybrid approach, taking the best of BBS, which I believe is the Peterson commitment part, putting that into the hash, making the hash much smaller, still using the snark, still being, supporting legacy, just a different string format. Anyway, I think we're out of time.
Yeah, exactly. Let's take any additional questions offline.
Thank you for your attention.